here today from a place called the Joint Quantum Institute, which is joint between the National Institute of Standards and Technology, which is the place I work for, and the University of Maryland, where I also do some teaching. And we've joined together to form this Joint Quantum Institute. And I'm part of the Laser Cooling and Trapping Group at the National Institute of Standards and Technology. And it's a great pleasure for me to work on a daily basis with Gretchen Campbell, Paul Lett, Trey Porto, and Ian Spielman, and a large number of young people who come from all over the world. And as you've heard, two of them are here with us today. Karina and Neil are members of our group, and we're very happy to have them with us as well. Probably providing support during this lecture, so that their jobs are very important today as well as every day in our laboratory. Well, I'm here to talk about time, Einstein, and the coolest stuff in the universe. Well, what does time and Einstein have to do with each other? Well, for one thing, Time magazine put Einstein on their cover as the person of the century. And I think it was a very good choice because Einstein discovered many things that changed the way we think about our natural world. He discovered how to explain the photoelectric effect. When you shine light on a metal, electrons come off. And he explained how that process works by saying, let's think of light as a stream of particles. Now, people had rejected the idea of light as being a stream of particles many years before, and in fact had spent the previous century proving that light was not a stream of particles, that it was in fact a wave. And Einstein comes along in 1905 and says, well, yes, it is a wave, but let's think of it as a particle as well. And this was a revolutionary idea, because now we understand that everything is both a particle and a wave. And this was one of the beginnings of what we now call quantum mechanics. And quantum mechanics has changed everything about our daily lives. Most of the technology that we have today in the form of cell phones and iPads and iPods and personal computers comes because of quantum mechanics. So this is a really big thing, and Einstein got the Nobel Prize for that. But in the same year that he figured out the photoelectric effect, he also explained Brownian motion. If you look at a drop of water that has suspended in it tiny particles of dust, you will see that the dust particles will be moving around. The reason, as Einstein explained, is the water molecules are moving around. They are in constant thermal motion, and they strike the dust particles and make dust particles move. Einstein's explanation, a quantitative explanation that was tested by experiment, was the thing that finally convinced everyone that matter is made up of atoms and molecules. Can you believe that at the beginning of the 20th century, not everyone understood or believed that matter is made up of atoms and molecules? And it was Einstein's treatment of Brownian motion that convinced everyone. But probably the thing that Einstein is most famous for is special relativity. Special relativity changed the way we think about space and time. And the way Einstein came to his understanding about special relativity was that he asked himself a question that I think people have been asking themselves since the beginning of time. What is time? What is this strange thing that is always the present, but is always moving to the future and soon becomes the past? What is time? Einstein thought about that question, and this is the answer that he gave. Time is what a clock measures. Well, you may think that that is a superficial answer, but by taking seriously the idea that time is what a clock measures, Einstein was able to come up with his theory of special relativity that changed how we think about time as well as space. But if time is what a clock measures, then we might ask ourselves, what is a clock? Well, for me, a clock is something that ticks, something that gives a periodic series of events. And people have thought about clocks in many different ways and thought about the kinds of things that clocks can do for us. Here is one example. Well, as the song tells us, time can come from a clock. Perhaps the earliest clock was the sun, as the song reminds us. Early people watched the rising and setting of the sun because of the rotation of the Earth, and the rotation of the Earth provides you with a ticker. Well, you know, things never work as well. The Earth is supposed to be rotating, and it works perfectly in practice. But anyway, the rotation of the Earth makes us see the sun rise and set, and ancient people were able to tick off days. More sophisticated ancient people made sundials, and in this way they were able to tick off hours. According to legend, one day Galileo was in church in Pisa, and he was watching the chandelier in the church swing back and forth. And he realized, and that chandelier swung much better than the animated one in my slide. He was watching the chandelier swing back and forth, and by making careful observations, he understood that the period, the time it took for the pendulum to swing back and forth, the chandelier, was independent of how far it was swinging. And that gave people the idea that a pendulum would make a good clock. And so we have pendulum clocks like this that keep excellent time and are also really quite beautiful. Some of you may be wearing a clock on your wrist, and inside that quartz watch is a tuning fork-shaped quartz crystal, and the vibration of that quartz crystal is the ticker for that quartz watch. Now, throughout history, clocks have been getting better and better, and in fact, it is one of our jobs at the National Institute of Standards and Technology, just as it is the job of CNAM here in Mexico, to make better clocks, because we have the responsibility for providing the standards of measurement, and one of those standards is the standard of time. And so we have been interested in making better clocks, and throughout history, clocks have been getting better, and some of these clocks have been not only marvelous works of engineering, but also works of art. Here is one of my favorite clocks. This clock is imaginatively named H4. The H is for John Harrison, who is the maker of this clock. And the reason he made this clock was he was trying to win a prize that was offered by the British government in the beginning of the 18th century, a prize for anyone who could determine their longitude on a voyage from Great Britain to the West Indies, not so far from here, with an accuracy of 30 miles. Harrison realized that if he had a clock that was synchronized to Greenwich time, that if he set his clock to noon when the sun was highest in Greenwich, and then took that clock with him on a voyage and noted the time when the sun was highest where he was, so that it was noon there, the difference in the time tells you how far east or west you are of Greenwich. You know, if you call someone in California, that the time is earlier. And if you call someone in Europe, the time is later. Well, Harrison realized that if he made a clock, then he could tell his longitude. And the requirement was, to win the prize, was that the clock had to be accurate for 2 to 2 minutes on this voyage from the United Kingdom, what is now the United Kingdom, from Great Britain to West Indies. That's not an easy thing at the beginning of the 18th century. There were sailing ships. Clocks at that time were made with pendulums. Imagine how a pendulum works on a sailing ship, an 18th century sailing ship. The ship is going like this, and the pendulum is going like that, and the clock is straight. You couldn't take a pendulum clock on a ship. You had to make something else. And Harrison spent his entire life trying to figure out how to make a clock that could do the job. And this was his fourth clock, hence H4. And this was the clock that in time trials, in the year, let's see, first I should tell you why was the British government interested in knowing the longitude. In 1707, the ship, the Association, and two other ships under the command of Admiral Sir Fowlsley Shovel, what a name. Those ships went onto the rocks, and the ship sank, and almost all of the sailors on board died. 1,600 sailors died, as well as the lost 3 ships. Why? Because they knew where the rocks were, but they didn't know where they were, because they couldn't tell their longitude. So this was an extremely important problem. Ships were being lost all over the world, and the British government decided to offer a prize of £20,000 sterling. Now, at the beginning of the 18th century, £20,000 sterling is not a small fortune. It is a huge fortune. This was how much it was worth for them to know what the longitude was, and Harrison spent his entire life trying to make a clock that would do the job. And in time trials in 1762 and 1764, he showed that his clock was accurate to 39 seconds in 47 days. 47 days was the length of the trip, and his clock was accurate to 39 seconds. Today, your quartz watch is certainly much better than Harrison's clock that was worth £20,000, a great fortune in those days. But all of the clocks that we have are imperfect. The swinging of a pendulum will change if the length of the pendulum changes, and temperature may change the length of the pendulum. Your quartz watch may keep different time if you wear it on your wrist or if you keep it on the table beside your bed. Even the rotation of the Earth is not constant. The fact that the rotation of the Earth varies is something that was made clear to me in a rather dramatic way one day when I was visiting the United States Naval Observatory. The U.S. Navy is interested in time for much the same reason that the British Navy was interested in time back in the 18th century, for navigation, and we'll talk more about that in a moment. But I was visiting a friend who was going to show me the latest clocks, and as we were walking along the hall, we passed by a door, and on the door was written, Director of Earth Rotation. Seems like a rather responsible job. You wonder what happens if that guy goes on vacation. The point is, someone keeps track of the variations in the rotation rate of the Earth in order for people who still navigate using the stars, and for people who still want to keep time according to Earth rotation, that time is consistent with the more accurate time that they keep with much better clocks. Well, what are those much better clocks? Well, to have a better clock, you have to have a better ticker. And the best tickers are atoms. Atoms have energy levels, and the spacing between those energy levels corresponds to a frequency. And that frequency can be used as the ticker for an atomic clock. And one of the great things about atoms as tickers is that while every quartz crystal in every watch is a little bit different, it keeps a little bit different time than every other watch and constantly has to be reset. The atoms are the same no matter where the atoms come from. Every atom of cesium-133, the atom that by international agreement defines what we mean by a second, a certain number of vibrations or oscillations of that atom, define what we mean by a second. Every single cesium atom in the universe is identical, absolutely identical to every other cesium atom in the universe. And that makes these things wonderful clocks. They're completely consistent, and they're very little affected by things like temperature and humidity, and all the other environmental effects can be easily controlled in these kinds of clocks. Well, how much do these clocks cost? Well, for less than $100 US, you can buy a quartz crystal watch that is good to a part in a million. That would be about 30 seconds in a year. But if you pay $100,000 US, you can get a clock that is good to a part in a million, 30 seconds in a million years. Now, okay, you're laughing. But think about this. You pay 1,000 times more money, and you get 1,000,000 times better performance. That sounds like a bargain to me. But still, you might ask yourself, who needs a clock that is that good? Because, after all, very few of us need to know what time it is in order to go about our daily lives. Or, so you may think. In fact, I would like to convince you that you do need at least somebody to know what time it is to that level of precision in order to do many of the things that you do in your daily life. I once found this advertisement in a magazine for a very expensive car. And it says, if you get into trouble in this car, no problem. Help is only 10,000 miles away, 16,000 kilometers in proper units. And what they're referring to is the orbiting altitude of the satellites of the global positioning system, the satellite navigation system. There is a constellation of satellites orbiting the Earth, at least 24 satellites at all times. And on every one of those satellites are several atomic clocks that keep time at the level of a part in a million. Now, how does this work? Well, let's imagine that you have a number of satellites in the sky, and each of them has atomic clocks on board, and they are all synchronized, so they're keeping exactly the same time. And there's a clock on the ground that synchronizes all these clocks. Now let's imagine for the moment, even though this is not the case, let's just imagine for the moment that you have a GPS receiver, a global positioning system receiver, and that receiver has a similar clock, and it is also synchronized. So all of these clocks are keeping exactly the same time. And these clocks, the ones in the satellites, are broadcasting what time it is. And you receive the signal telling you what time it is on that satellite. Now, all the clocks are synchronized. But it takes a certain amount of time for the signal to go from this satellite to you. And so you will read a time that is earlier than the time that you have on your own clock because of the delay of the signal getting from the satellite to you. And each of the satellites has a different delay because each satellite is a different distance away from you. Now, the satellites also know exactly where they are because they're being tracked by ground stations. And they broadcast that information as well, the information about where they are. Now, if you know how far away you are from three things, and you know where those three things are, you know where you are. And that's how the global positioning system works. So anytime you see three satellites, you can tell where you are. But there's a problem. You don't have a clock. And that's why you need a fourth satellite. So anytime you can see four satellites, the fourth satellite basically acts as your clock. So anytime your global positioning system receiver can see four satellites, it can tell where you are, any place on the face of the Earth, to a distance of a few meters. Now, what do these atomic clocks look like? Well, first of all, let me say, this global positioning system is something that you rely on a lot. Taxis in big cities often have global positioning systems. Delivery trucks have GPS systems. When you fly in an airplane, they're using the GPS system to navigate between airports. So you definitely need this kind of atomic clock. But we might ask ourselves, what do these atomic clocks look like? Well, here's another advertisement that I saw in a magazine. It said that scientists in Braunschweig, Germany, this is another place where they have a metrology laboratory like CNAM, like NIST, that they've set their atomic clocks back by 1 full second. And this is an advertisement for an airline. They claim their schedules have been adjusted accordingly. Yeah, right. But the thing that I want to point out is that the instrument in front of which these two dorks are standing looks nothing like an atomic clock. If you were to go to our laboratories, our atomic clock laboratories in Boulder, Colorado, you would see an instrument that looks more like this. So what is inside this long tube? Well, for one thing, there is a vacuum enclosure, and inside that vacuum is something that schematically looks like this. Here is a can, and that can contains some cesium metal. Now, you may remember from your chemistry classes that cesium is an alkaline metal that is over on the left-hand side of the periodic chart, down towards the bottom. It's an extremely reactive metal. It burns in air, but this is in a vacuum, so we don't have to worry about it burning. We heat it up so that it melts and vaporizes. And from the vapor, we get atoms of cesium, and some of those atoms of cesium come out a hole inside of the can and make a stream of atoms that we call an atomic beam. Now, cesium, remember, is the atom that we use to define what we mean by a second. So this is a good atom to use for a clock. And the ticking of the atom is synchronized with the ticking of your laboratory clock, something that is much like your quartz watch, but of very much higher quality. And you synchronize the ticking of the laboratory clock with the ticking of the cesium atom here, at the beginning of this apparatus. This is much like what would happen if you want to synchronize your watch to the correct time. I suggest you go to www.nist.gov, my organization, and on the left-hand side of the home page is an icon for getting the correct time, and an animated clock will pop up, and you can set your watch to the time better than 1 second. Well, that's good, but it's not enough. It doesn't keep your watch running at the correct time. You have to know how fast or slow your clock is so you can make a correction. Now, that's what's done at the other end of the apparatus. At the other end of the apparatus, you measure again, just like if you were trying to see how fast or slow your watch was, you would make another measurement later. How much later? Well, it would be useless to make a measurement 1 minute after you made the first measurement, because not enough time would have elapsed for you to tell the difference between the ticking rate of your watch and the correct time that's broadcast by NIST. I check my watch every month, and in that way I can tell exactly how fast or slow my watch is and make a mental correction. That's what us geeks do. But that long time is a problem, because in this experiment, the cesium atoms are moving faster than 100 meters per second. And the apparatus is less than a meter long. So that means there are only a few thousandths of a second between the time when you make the initial measurement, the synchronization, and the time when you make the final measurement, the comparison, to tell what is the difference in the ticking rate between the laboratory clock and the atomic clock, which is keeping perfect time. The atoms are keeping perfect time. And then you see what the difference is, and you make an adjustment. Now, it's really difficult to do that for such a short time, but people have been working on this for 50 years. And they've learned all sorts of tricks. And they've been able to make these clocks good to better than a part in 100 million. But our job is to do the best we can. And a part in 100 million is not good enough for us. We want it to do better. So what are the things that limit the performance of the clock to a part in 100 million, a part in 10 to the 14? Well, one of those things is the Doppler effect. Let's imagine you go to the seashore, and there are waves coming in to the beach. You could time the waves and find out what the frequency of the waves hitting the beach is. Now, you could get into a boat and head into the waves and measure the frequency as the waves hit your boat. That frequency will be higher because you're moving into the waves. That's the way the Doppler shift works for ocean waves. It works the same way for sound waves, and it works the same way for light waves. If you're moving towards the source of the waves, and you can think of that source of waves as being a clock, it gives you a set of periodic events. If you're moving towards the source, or if the source is moving toward you, the frequency, the ticking frequency, will be higher. And if you're moving away, the ticking frequency will be lower. This, by the way, is how the police tell how fast your car is going. They shine microwaves at your car. They bounce off. Your car is now a moving source of microwaves. They look at the difference in the frequency that comes from your car compared to the frequency they send out, and that tells how fast you're going. How big an effect is this? Well, a typical atomic velocity, for example, the molecules in the air in this room, is about 300 meters per second. The velocity of light is 300 million meters per second, and the fractional Doppler shift is the ratio of the velocity of the moving source or the moving receiver and the velocity of light. So that's on the order of a part in a million. That's a disaster. We're trying to make clocks that are good to a part in 100 million, and the Doppler shift is giving us shifts that change the frequency by a part in a million. Well, people have come up with all sorts of wonderfully clever tricks that get rid of this by canceling out the Doppler shift going in two different directions. And in this way, they've been able to get to a part in 10 to the 14. But the part that they haven't been able to get rid of, a part in 100 million of the Doppler shift, the inability to correct for that last little bit is one of the things that limits our ability to make better clocks. But that's not all. Remember, Einstein changed the way we think about time. One of the things he showed was that a moving clock runs slow. And what that means is that if you're moving, your own time runs slow. This leads to amazing ideas. Imagine that there were a pair of twins sometime in the future. And the twins grow up and choose careers in science, but different paths. One of them chooses to be a theoretical physicist, and he goes to work for the Polytechnic Institute and does theoretical physics. The other one decides that she is going to do something more practical and joins the astronaut corps and goes off on a trip in a spaceship. Remember, this is the future. And the spaceship travels at close to the velocity of light. She goes off for a couple of years on a science mission, traveling at close to the velocity of light, and comes back and wants to have a visit with her brother that she hasn't seen in a few years. She goes to visit him, and she finds that what little hair he has left is now white, that he's old and decrepit, he's retired, but he's still working because that's what physicists do. Whereas she is still young and vigorous. Why? Because time has run slower for her. How much slower? Well, it's the ratio of the square of the velocity to the square of the speed of light. So for thermal velocity, it's quite a small effect, a part in a million. But there aren't any tricks to get rid of this. And so you have to measure the velocity of the atom and make a correction. And the inability to do that perfectly is another one of the things that limits the performance of these clocks. So the things that limit the performance of a clock are we don't have very much time to make the measurements because the atoms are going so fast, the Doppler shift because the atoms are going so fast, and this relativistic change in time itself because the atoms are going so fast. So what is the solution? Make the atoms go more slowly. And that means cooling them down, because the difference between hot and cold is how fast the atoms and molecules that make up the stuff that is hot or cold is. So, for example, the air in this room is pretty hot. I'm feeling kind of hot myself right now. The molecules are moving around at about 300 meters per second, the speed of sound. If we could cool the air in this room down, which seems like a good idea, it would mean that the atoms and molecules would be moving more slowly. Now, to give you an idea of just how cold we'd like to get things and just how slow we would like to get things, I've brought along some really cold stuff. Inside here, inside this big bucket, which we call a dewar, it's really just a big thermos bottle, is liquid nitrogen. Now remember, nitrogen is the major constituent of the air. Most of the air is nitrogen. And this is liquefied nitrogen. It's been cooled so much that the air has turned into a liquid. Compared to this, the floor on which I'm standing, this table on which I have these flowers, is so hot that contact with this table will make the liquid nitrogen boil. So when I pour it out, it boils. Think what would happen if you were to pour water onto a red-hot stove. It would boil immediately. And that's what happens when I pour the liquid nitrogen on the floor. Now, I wish there was more room. I would I'm getting a really exciting view of how cold this liquid nitrogen is. But this is really, really cold stuff. So you might think, oh, let me pour some over here for the people on this side. This is just such marvelous stuff. I want you to see how wonderfully cold it is. So you may think, what do you mean it's so cold that it boils? What it means is that its boiling point is so low that when you pour it out onto the floor is so hot that it makes it boil immediately. Now, if you've got something that's that cold, then you might think that it's a reasonable idea to use it to cool down a gas to make the atoms and molecules move more slowly. And that's exactly what we're going to do. What I'm going to do is put some warm gas, some hot gas, into this bucket here that I just poured some liquid nitrogen into. So here we have a traditional container for hot gas. So what I'm going to do is blow it up and put it into this bucket that is full of liquid nitrogen. The idea being that if I can make the gas in this balloon cool down, then the atoms and molecules will be moving more slowly, and if we then wanted to make measurements on them, we could make better measurements because the atoms and molecules will be moving more slowly. Now, what else can I do to show you how cold this stuff is? Here is another thermos bottle. It's been sitting out in the room all day. It's hot. It's incredibly hot compared to the liquid nitrogen. If I were to take a metal bucket and heat it up in a fire until the bucket was red hot, and then poured cold water into the bucket, what would happen? The hot bucket would make the water boil, which is what's happening here. So let's let that boil away. And while it's cooling down, let's cool down some more gas. Because if you want to do experiments, you want to have lots of stuff to do experiments with. And so let's make more gas colder so that the atoms and molecules will slow down so that we can make better measurements, because we'll have a longer time to make the measurements if the atoms aren't moving so fast and moving out of our apparatus. Okay, so let's look here. Okay, the boiling has subsided, but a lot of the liquid nitrogen has boiled off. But fortunately, I've got more. So let me top it up. And now, let me take one of these lovely carnations, fresh carnations this morning. Nice, fresh carnations. And what I'm going to do is I'm going to plunge this carnation into the liquid nitrogen. Now, what will happen? Well, imagine that you took something like a fireplace poker, something you use to move the logs around in a fire, and you put it in the fire until it is red hot. And then you take it out and plunge it into a bucket of cold water. What will happen? It will make the water boil, which is what we're seeing here. So the water is, the liquid nitrogen is boiling away because the flour is so much hotter than the liquid nitrogen. It's hard to keep it in. Okay, so now the flour is causing the liquid nitrogen to boil. So while that's boiling away, let's cool down some more gas. Because we want to make the atoms and molecules move more slowly. And that gives us longer time to look at them, of course. It also makes the Doppler shifts of the energy levels be smaller, and makes it easier for us to measure the ticking frequency of the atoms and molecules, so in order to make a better atomic clock. So now I look in here and I see that the boiling from the carnation has subsided. That means that the temperature of the flour is now down to the temperature of liquid nitrogen. When I take this flour out, it is so cold that I can crush it like it was made out of glass. This stuff is really, really cold. And if you've got something that's that cold, then why not use it to cool down your gas to make the atoms and molecules move more slowly? So, okay. Now let's see, what else can I do to illustrate how cold this stuff is? Here, I have a rubber band. Nice, stretchy rubber band. So what I'm going to do is take the rubber band and dip it into this styrofoam box, which has liquid nitrogen in it. Now you can't see it, but as with anything that's room temperature that goes into liquid nitrogen, it's making the liquid nitrogen boil. But it doesn't take too long before the boiling subsides. And now, when I take out the rubber band, it is frozen so hard that I can break it like it was a dry twig. But if I just warm it up in my hands a little bit, nice, stretchy rubber band. So what else? I'm sure that when you were young, your mother told you, because all of our mothers tell us what we should do, and they're always right. Your mother told you you should never take a closed container of liquid and put it into the oven. So now we have some liquid in the container. And now, I'm going to close it. I'm going to put the lid on really tight. And compared to this liquid, this room is an oven. So now, I have a closed container of liquid in an oven. Let's see what happens. Now, what else can I do to show you how cold this stuff is? Here's a racquetball. Nice bouncy racquetball. I'm going to put it into the liquid nitrogen. And while that's cooling down, let's cool down some more gas. We will have lots of gas. None of what you're laughing about. Now, this stuff is incredibly cold. You know, it made the flowers turn into something like glass. It made the rubber band break like it was a dry twig. How cold is this stuff? Well, physicists like to measure the temperature of things, not in the Celsius scale, but in something we call the Kelvin scale, where we measure up from the coldest temperature you could possibly have. Now, that temperature is what we call absolute zero. Now, why is there a coldest temperature that you could possibly have? Well, just look at this cartoon of the difference between hot and cold. The difference between hot and cold is how fast the atoms are going. In fact, the temperature is proportional to the kinetic energy of the atoms, which goes like the square of the velocity. So if it's colder, that means the atoms are moving more slowly. What's the slowest you can go? Well, the slowest you can go is stopped. So that means there is a lowest possible temperature when the atoms stop moving. Now it turns out that because of Heisenberg's uncertainty principle in quantum mechanics, that even at absolute zero, the motion doesn't stop. But let's just say that between friends, that at absolute zero, the motion stops. So there's a lowest possible temperature. We call that absolute zero. And on the scale where zero is that absolute lowest temperature, room temperature is about 300 degrees, 300 Celsius degrees above absolute zero. Ice melts at about 273 degrees. The coldest temperature that anyone has ever measured anywhere on the face of the Earth for an air temperature was 185 degrees above absolute zero. This was in Antarctica sometime during the winter. They measured 185 degrees above absolute zero. This stuff, which is so cold, that when you pour it out on a surface, it boils immediately. This stuff is 77 degrees above absolute zero. Well, actually, it's even colder here in Mexico City because the pressure is lower, and that makes the boiling point even lower, just like it does for water. So I'm not sure what it is in Mexico City, but it's probably at least 75 instead of 77. If you have not been in a low-temperature physics laboratory, this is the coldest stuff you've ever seen. And as we've been saying, it seems perfectly reasonable if you've got something that cold that you might as well use it to cool down your gas, so the atoms and molecules are moving more slowly. Oh, I must have made it too big. Have to sort of force it in. Oh, there we go. Okay, just have to push harder. Okay, let's see what happened to our racquetball. So you remember the nice bouncy racquetball that we had before. Let's see what happens to this one. It breaks like it was made out of China. I think there's a little language problem. You see, in the United States, China means porcelain. I'm thinking that the quality has something to do with its origin. I didn't mean that at all. Not at all. But you can see that this stuff is really, really cold. And so it's perfectly reasonable to use it to cool down our gas to make the atoms and molecules move more slowly. But I believe that a few of you who are particularly perceptive have noticed that the volume of balloons that I put into this bucket was in fact considerably greater than the volume of the bucket. And the reason is that these balloons are as flat as pancakes. Does anybody remember how many balloons I put in? 6, 5, I don't know. How many have I taken out? How many white balloons did I put in? How many yellow balloons did I put in? How many orange balloons? Always remember what your mother told you. Never, ever put a closed container of liquid into an oven. That's what happens. Because compared to the liquid nitrogen, this room is like an oven. And it seemed like it was a good idea to cool down our gas with liquid nitrogen, but in fact it's not such a good idea, and the reason is that those balloons collapse. Why? Because if you take any gas, put it in contact with a refrigerator, that is, put it into a container, put the container in contact with the refrigerator, that's how we refrigerate things. We put them in a container. We put the container into the refrigerator. That's how you make beer cold. If you do that and make it cold enough, it will condense into a liquid or a solid, or the gas will stick to the walls of the container, and you will not have a gas anymore. And if you don't have a gas, then the atoms are going to be stuck onto other atoms or the wall, and they won't have the perfect ticking frequency that you want in order to make a wonderful clock. So we can't use ordinary refrigeration in order to make our atoms cold, because if we do, we won't have any free atoms left, and they won't have the right ticking frequency if they're in a solid or if they're stuck to the wall of the container. So how do we make something really cold without touching it? And the answer to that question has been staring at us from the heavens for centuries. Since the time of Kepler, people have known that the tails of comets always point away from the sun. So if you have a comet coming from somewhere out in the outer reaches of the solar system, as it comes in, it gets warmed up by the sun, and the dust and gas that are frozen in the comet are liberated, and the sun pushes on the dust and gas and pushes the tail away, so the tail streams behind the comet. But as the comet comes around the sun and heads back out to the outer reaches of the solar system, the tail streams in front of the comet. Because the light is pushing on the dust and gas, light pushes on stuff. Now, for comets, there's also a solar wind that pushes on them. But the point is that light exerts a force on things. And what we're going to do is to use the pressure of the light to push on the atoms to make them slow down. Now, in order to understand how that works, I need to tell you about two things. One of them is called resonance. If I have a gas of atoms and I shine light into it, typically the light goes right through the gas. The gas is transparent. The air in this room is transparent to light. That's why we can see one another. That's why this laser pointer can go from the laser to the screen without being weakened, because the air is transparent to the light. But for certain kinds of gases and for certain colors of light, the gas is not transparent. For example, let's say that I have a gas of sodium atoms. You, in fact, have seen gases of sodium atoms. If you look at these yellow street lamps, they have inside them a gas of sodium atoms. If you shine a laser that is tuned to the yellow color that those sodium lamps emit, it will be absorbed by the gas. And when it is absorbed by the gas, the atoms will feel a force on them in the direction of the laser. If the light is not absorbed, there will be no force. The light must be resonant with the atoms. That's the idea of resonance. The light must be resonant with the atoms in order for the atoms to absorb the light, and when they absorb the light, they'll feel force. The other thing you have to know about, we've already talked about, the Doppler shift. If you have a wave and you're moving toward it, then that means that the frequency of the wave is higher, the color is shifted from the red toward the blue. If you're moving away, it'll be shifted in the other direction. These are the things that you need to know. Now, this Doppler shift, as we've seen before, is quite small. It would be a really bad idea if you were to go through a red light and be stopped by the police. Does that happen here? And to explain to the police officer that, in fact, because you were moving toward the red light, that it looked green. In order for you to see that kind of a color change, you would have to be moving at close to the velocity of light. And I think the speeding violation will be worse than the red light violation. So, the atoms, on the other hand, are so exquisitely sensitive to the color that they can tell even the tiny change in color that you would never be able to see. They can tell that tiny change in color from the velocities that they're moving at. So with those two things in mind, let's see how laser cooling works. So let's imagine that I have a gas of atoms, represented here in one dimension by an atom going to the right and an atom going to the left, because in a gas, the atoms are going in every direction. Now let's bring a laser beam in from the left, and let's tune the frequency of the laser so that it is a little bit lower than the frequency that is resonant with the atoms when the atoms are at rest. A little bit lower in frequency, which means a little bit redder in color, but so small a change in color you would never be able to tell, but the atoms can tell. An atom at rest will not absorb very much light from this laser, but an atom moving in this direction will see this laser beam shifted up in frequency, and therefore it will absorb the light and slow down. An atom going this way will look back at the laser and say the frequency is even redder than it was when I was at rest, and then it won't absorb very much light at all. If it does absorb, you see it gets speeded up, but that doesn't happen because the color is wrong. Now, just bring in the laser beam from the other side. This atom going this way sees this laser beam as being resonant and it slows down. This atom going this way sees this laser beam as being resonant and slows down. So no matter which way the atom goes, it sees the laser beam that opposes its motion as being the one that is in resonance, and therefore it absorbs selectively from the laser beam that opposes its motion. Now you just bring in laser beams from all directions, and no matter which way the atom goes, it always sees those laser beams that oppose its motion as being the ones that are closer to resonance. The atom feels as if it is in a viscous fluid. If you were in a swimming pool full of molasses, then whenever you tried to move, you would feel that there was a force that opposed your motion. That's the way the atoms feel. And understanding that connection between the atom's behavior in this light field and the way a particle like you would behave in a viscous fluid, Steve Chu called this optical molasses when at Bell Labs he did the first experiment like this, bringing laser beams in from all directions back in 1985. I'll remind you, Steve Chu is the Secretary of Energy now. How hot are the atoms? Well, if the story about atoms slowing down because of the Doppler shift was all there was to it, then the atoms would simply come to rest. But that's not what happens. And it doesn't happen because of what Einstein told us in 1905. Remember, Einstein got the Nobel Prize for explaining the photoelectric effect, that light is like a stream of particles. That means when an atom absorbs light, it absorbs light one particle at a time. And we call those particles photons. So imagine that I am an atom and I happen to be at rest. And there are laser beams coming from that side and from that side. And let's imagine that the laser beams have exactly the same frequency and exactly the same intensity. It is equally likely that I will absorb light from that side or from that side, but I will absorb it from one side or the other. And when I do, I will get a kick. And it is completely random which direction that kick will be in. Let's imagine that this time I absorb a photon coming from that direction. I will get a kick like this. And I'll now, on the sodium atom, which is the first atom we used in our experiments, I'll be moving at about 3 centimeters per second. Now, because I absorbed the light, I'm excited, can't you tell? And I want to get rid of that extra energy, and I do that by emitting a photon. And it's just like shooting a gun. There's a recoil. And I change my velocity by 3 centimeters per second. Now, I'm back down to the lower energy state. I can absorb another photon. Randomly, maybe it comes from this side, and I get a kick like this. And then this time, maybe I emit the photon in a random direction. It goes that way, and I get a kick like that. Every time I absorb or emit a photon, I get a kick in a random direction, and the atom is doing this kind of random dance, and that keeps the atom up. At the same time, if the velocity of the atom by chance starts to go in one direction, the Doppler shift will reduce that velocity, and there's an interplay between the cooling due to the Doppler shift and the heating due to the randomness of the absorption and emission, and the atoms come to an equilibrium. And the equilibrium for sodium atoms is at a temperature that can be as low as 240 millionths of a degree above absolute zero. 240 millionths of a degree above absolute zero. Remember, this stuff, which is so cold that it boils when I pour it out on the table, this stuff is 77 degrees above absolute zero, and it's the coldest stuff you've ever seen. And we're talking about getting down to temperatures of 240 millionths of a degree above absolute zero. People got very interested in this idea, and we started doing experiments, and Steve Chu started doing experiments, and here is a picture taken in our laboratory showing optical molasses, laser beams coming in from all different directions, and this is about 1 centimeter across, and it contains about 100 million sodium atoms with a temperature that could be as low as 240 millionths of a degree. Now, how do you measure the temperature of something that is supposed to be as cold as 240 millionths of a degree? You can't exactly take a thermometer and shove it up into the gas. What we do is we measure the temperature by measuring how fast the atoms are moving. So here is what Steve Chu did in his first experiment. He put the atoms into these cross laser beams, the optical molasses, and now the atoms are moving around with some velocity that we want to determine. The laser beams are then turned off, and now the atoms are free to expand in the vacuum, just as any gas would. After letting the atoms expand for a few milliseconds, a few thousandths of a second, you turn the laser beams back on, and you recapture some of the atoms. Now, by knowing how big the atom cloud is, and by knowing how long you allow the atoms to move before you turn the laser beams back on, you can figure out how fast the atoms are going and what their temperature is. And when he did that, he got 240 microkelvin with a big uncertainty. Now, this was wonderful, because remember, 240 microkelvin is the lowest temperature that the theory says you can have by the balance between the cooling and the heating. We repeated that experiment a little bit later, and we repeated it in exactly the same way, and we got exactly the same answer, 240 microkelvin. And other people in other laboratories with other atoms repeated the experiments and found the temperatures that were expected for those atoms by this theory. So everyone was happy, until we started to make some more measurements. We started to measure how sticky is this molasses. And we found that it was a lot stickier than it was supposed to be. And we couldn't understand it because the theory was quite simple. So we worked very, very hard on the theory, and we couldn't come up with any explanation for why the molasses was more sticky. And then we thought, in fact it was Paul Lett in our group who said, maybe if we measure the temperature more carefully, we'll get a clue about what was going on, because the temperature measurement was very difficult, and it had a large experimental uncertainty. So we thought, let's develop a new method for measuring the temperature, and I wish I had time to tell you about all that, but when we did that, quite unexpectedly, we found that the temperature was much lower than the theory predicted it was possible. In fact, the theory said it could be 240 microkelvin. We measured 40 microkelvin, 6 times lower, not just a little bit lower, but 6 times lower than what the theory said was possible. In later experiments, we got to 200 times lower than what the theory said was possible. Remember, the whole point was to make the temperature as cold as we could. And apparently we had made it colder than we could. This is clearly a violation of Murphy's Law. When we did this, we felt very much like the guys in this cartoon who have found something that is far colder than is allowed by the environment in which they're working. And so there were many discussions about what to do about this. Other people repeated our experiments and confirmed that the temperature was much colder than the theory said was possible, so people had to come up with a new theory. And there were lots of discussions about what the nature of that new theory should be. Some people said we needed more cooling, and some people said we needed less heating. Well, that kind of thinking didn't really help very much, but it didn't take too long before Paul Cohen-Manucci and his young colleague Jean Dalibard figured out what was going on. And I wish I had time to tell you about that too. But guided by that new theoretical understanding, we, by 1995, were able to pull cesium atoms. Remember, cesium are the atoms that define what we mean by time. We cooled them down to 700 nanokelvin, 700 billionths of a degree above absolute zero, 7/10 of 1 millionth of a degree above absolute zero. This stuff, which is the coldest stuff you've ever seen. It boils when I pour it out of the ground. Oh dear. But fortunately, I've got more. This stuff is the coldest stuff you've ever seen. It's 77 degrees above absolute zero. 77 degrees above absolute zero. We're talking about having achieved a temperature that is 100 million times colder than this stuff, which is the coldest stuff you've ever seen. So, having gotten that, what kind of a clock can you make? Let me remind you of the problem with the old clock. You had an atomic beam moving at faster than 100 meters per second. You synchronize the ticking of the atoms here. You compare that to the ticking of you synchronize with your laboratory clock. You compare it to the laboratory clock at the other end of the apparatus, and the time required was just a few thousandths of a second. And that shortness of that time, along with the Doppler shift, were the things that made it difficult to make a better measurement of the time. Now we have atoms that are moving so slowly at 700 nanokelvin. The velocity of the atoms is less than 1 centimeter per second. So they're 10,000 times colder. 10,000 times slower than the atoms in the original experiment. What kind of a clock can we make when the atoms that we put in here are only moving at 1 centimeter per second? And the answer is no clock at all, because the atoms drop like stones. If you have something that is moving at 1 centimeter per second, it will go straight down. And that's what our atoms did. But fortunately, more than 50 years ago, at MIT, a guy named Gerald Zacharias had figured out what to do. And what he said was, toss the atoms up. Instead of having a 1 meter long apparatus that's horizontal, have a 1 meter long apparatus that's vertical. In fact, he suggested even a longer distance. And watch what happens if you toss something up 1 meter. It comes back after 1 second. So instead of a few thousandths of a second, you get a whole second to make your measurement. Here is a picture of what is called now an atomic fountain clock. An atomic fountain because it's like these water jets that go straight up and fall back down. The atoms go straight up. They interact with the local clock on the way up. They come back down and they are checked by that same local clock on the way back down. And with that 1 second interaction time, these clocks have made huge improvements over what was possible with the old clocks. In fact, the best of these clocks have accuracies that are in the order of 3 times 10 to the minus 16. That is accurate to 1 second in 100 million years. And today, all over the world, metrology laboratories, including here in Mexico at CNAM, are using these kinds of clocks to keep the time for the entire world. 1 second in 100 million years. At the National Institute of Standards and Technology, this is what we call close enough for government work. Now, it's wonderful to have things that are that cold. In other kinds of clock experiments, we've gotten even better. Dave Wineland has made ions that keep time to a second in 3 billion years. And this is revolutionizing timekeeping. But you might ask the following question. Where do you keep the coldest stuff in the universe? This stuff is the coldest thing anybody has ever had. Where do you keep the coldest stuff in the universe? Well, let's say that you wanted to keep your atoms in some kind of container, like this bowl. And let's imagine that the bowl was cold as the atoms. Well, then what would happen would be the atoms would simply stick to the bowl, and you wouldn't have any atoms floating around, and you couldn't do any experiments. Well, what if the bowl is hot? Well, if the bowl is hot, it means that inside the bowl, the atoms and molecules are moving around really fast. They're going to hit the atoms, heat the atoms up, and you won't have any cold atoms anymore. So you can't use any ordinary bowl. What you have to do is use some kind of a container that does not have any material in its wall. And what we do is we use a container that is made out of a magnetic field. I hope that when you were kids that you played with magnets, because it's so much fun to play with magnets. Do you remember the first time you held two magnets in your hand and had them turned the right way so that they would repel each other without touching? I'm still amazed by that. Well, that's what I've done here. These magnets repel each other without touching. You can exert a force on a magnet with another magnet without touching it. That's what we're going to do to our atoms. We're going to use a magnetic field to make a magnetic bottle for our atoms, because it turns out that our atoms are like little tiny magnets. So let's go now to the video camera. So if you look on the side screens, here is a big magnet. Here is a little magnet, which represents our atoms. Now, I've arranged it so that this big magnet is pushing up on the little magnet. And right here, it's pushing up just hard enough to balance the force of gravity, so that if I let go of it, it should just float there. And when I do let go of it, what happens is that it does not float, that it flips over and it gets attracted to the big magnet. If you had a lot of magnets when you were a kid, you might have tried this yourself, to lay out a bunch of magnets on the table and see if you could make another one float above it. It never works. And the reason it doesn't work is because the magnet that you're trying to make float always flips over and gets attracted to the magnets that were pushing it up. But there's something else you learned as a child, which is that if you spin a top, it will not flip over. And it turns out that our atoms are spinning magnets. So I'm going to spin this magnet. And now I'm going to lift it to the place where the force of the magnetism counters the force of gravity. Now, I can do a little better than that. The temperature in the room has changed a little bit since we set this up, and that means that the strength of the magnet has changed a little bit, and so I have to adjust the weight of this thing a little bit to make it float at the right place. So let me just see if I can do that. Magnetic trapping. Let me show you the real thing.
Not on the screen.
Oh, okay, sorry. Whoops. Let's go to, I don't know what.
There you go.
Okay, so let me see if this is the right thing. Right, here we go. So this is, oh, it's not showing. What you're not seeing is this wonderfully brilliant cloud of atoms, about 2 millimeters across, bouncing, well, but it's still, bouncing back and forth in the trap, being held by magnetic fields in the same way that the toy top was being held. And the temperature of this cloud is about a few millionths of a degree above absolute zero. And this ability to hold atoms in a magnetic bottle has allowed us to do something else marvelous. We can hold the atoms in a magnetic trap and evaporate them. Now, when you evaporate water, it makes the remaining water colder. If your coffee is too hot, you blow on it. And what happens is that the most energetic water molecules escape from the surface of the coffee. And what's left behind is therefore colder because you evaporated the most energetic ones. Now we're going to do exactly the same thing by putting our atoms into a magnetic bottle and allowing the most energetic ones to evaporate. And when that happens, the temperature gets so low that we can do an experiment that Einstein suggested back in the early part of the 20th century. And I don't have enough time to tell you all about this, but Einstein predicted this amazing thing, that if you got the gas cold enough, most of the atoms would stop moving. In other words, you would have a large number of atoms that would behave as if they were at absolute zero. 1924, Einstein predicted that. It was in 1995 that a group of scientists in Boulder, Colorado, at NIST, at my institution, made a Bose condensate for the first time, Bose-Einstein condensate for the first time, and in 2001 they got the Nobel Prize. And here's Eric Cornell and Carl Wyman from Boulder, Wolfgang Ketterle from MIT, and here's a picture of their temperature measurements. And with those kinds of temperatures, they got down those first experiments to 50 nanokelvin. So now we are at the end of an odyssey on which we have been trying to get colder and colder temperatures. And to illustrate where we have been and where we might be going, I had this cartoon version of a thermometer, which is a logarithmic thermometer. In this logarithmic thermometer, every mark on the thermometer represents a factor of 10 change in the temperature. So at the top of the thermometer, we have the surface of the sun, 5,000 degrees. Not the hottest temperature in the universe by a long shot, but mighty hot, 5,000 degrees. On this thermometer, room temperature is only a tiny bit colder than the surface of the sun. And liquid nitrogen, this marvelous stuff, that's the coldest stuff you've ever seen. It is so cold that it boils when you pour it out on the table. This stuff is 77 degrees and only a little bit colder than the surface of the sun. In fact, if you go to outer space, the temperature there is the temperature of the black body radiation left over from the creation of the universe 14 billion years ago. And that temperature is about 3 degrees above absolute zero. That's the coldest natural temperature there is anywhere in the universe, 3 degrees above absolute zero. We are talking about, in the first experiment, getting down to 240 millionths of a degree, and then finally to 700 billionths of a degree above absolute zero, and then using evaporative cooling to only 50 billionths of a degree. Now, in recent experiments, the temperatures that have been reached are less than 1 billionth of a degree above absolute zero, 3/10 of 1 billionth of a degree above absolute zero. These temperatures are millions of times colder than the coldest natural temperature in the universe. And we have ideas for getting even colder by taking these experiments into space, where we won't have to worry about the difficulties caused by gravity. Well, it's not really the end of the odyssey. In a certain sense, it's only the beginning. What can we do now? Well, we've already made better clocks. Atomic clocks, atomic fountain clocks, like the ones that you saw in Boulder, like the ones that are in CNAM here in Mexico, are now keeping time for the entire world. Those clocks are now synchronizing the clocks on the GPS satellites, which are not laser-cooled yet, but they keep better time than those clocks, and they synchronize those clocks from the ground. Using clocks like this, we can make tests of the most fundamental theories of nature. For example, we can find out whether the so-called constants of nature are indeed constant by measuring different kinds of clocks against each other in ways that was never possible before. We use these cold atoms to simulate problems in quantum mechanics, problems about the nature of materials that we know how to do the problem, but we don't have any computers that are fast enough to get the solutions to those problems. Solutions to problems like what is responsible for high temperature superconductivity. If we could solve that problem, we might be able to make better superconductors. We might be able to help the energy problem. We can't do that because we don't have the capacity to solve those problems. Our cold atoms may be able to provide that missing link to solve those kinds of problems. Quantum computers, I talked about this on Monday, and quantum computers would have the capability of solving certain kinds of problems in a time that's very short compared to the time that ordinary computers would solve the same problem. In fact, problems that would take the age of the universe to solve on an ordinary computer might be solved with a quantum computer in a matter of hours. And perhaps the most important thing on this list is the last one, the things that we don't yet know about, the applications of cold atoms and of the kind of technology that I've been describing to you that has not yet been thought of. And as I look out at the young people in this room, I'm thinking that some of you young people may be the ones who come up with the most astounding new applications of this way of thinking about manipulating atoms and manipulating materials. And if you're interested in this sort of thing, then you might be able to join a group like ours, where young people from all over the world come to our group to do experiments, to share their knowledge and experience, and to learn from others from their knowledge and experience as we work on these cold atoms. And here in this somewhat old picture, I just want to point out that one of our postdocs, Eduardo Gomez, is now at San Luis Potosi as a professor at the university there. And in this more recent picture, here is Neil Corzo-Trejo. There's Karina Jimenez Garcia, who are sitting right here. And another one of our postdocs, Alberto Marino. In this picture, the non-U.S. country that is most represented is Mexico. We have people from all over the world, from France, from Germany, from China, but the most represented country is Mexico. And there are opportunities for working in our Joint Quantum Institute where there are opportunities for undergraduates, for graduate study, and for postdoctoral study. And I thank you very much and hope that I've been able to share